Okay, I thought maybe I'll go over some of these problems for B9. So we're going to use that as part of the quiz. First thing I'd like to bring up is the table. The table shows reactivity. So the reactivity is really when we have two monomers and we compare the reactivity of the two. Example one here is styrene, for example. The styrene we're going to have, let's see, over here. No, it didn't work. So styrene, we're going to look at the styrene, oh here it is, versus methyl methacrylate. So again, as you can see, methyl methacrylate styrene has the R 1.52 versus 0.46. So their reactivity wise are similar. Now if you look at the styrene and then vinyl acetate, you can see the styrene is really high, 555, and vinyl acetate is 0.01. So if you put them together for a styrene and vinyl acetate, it's really starting to react by itself and make the polymer. And maybe a little bit of the vinyl acetate goes in. Versus the first case, you probably have a mixture of the two, so that could be a repeating unit of these two monomers. So let's look at some of the problem we looked at during the lecture. Sorry. So if problem number one is asking us simple things like we have two monomers and we were asked to what would be the structure if you make a polymer as an alternative copolymer. So that means they're starting and we're looking at the starting and ethylene, so there would be repeating units. So when we start with the starting first, again, let me see if I can use this little arrow here. So we start with the starting, and then we put the ethylene in, and then we follow that by the starting. So again, repeating units require alternative copolymers. Now, in example B, we were asked to look at the block copolymers. The block copolymers, if you remember, is when we have one series of mer from one monomer and that repeats with the second one. So if you look at this example here, we can see that we propose to use uh, isobutylene, no, consider propylene, sorry, propylene, and then we add to propylene the vinyl chloride. So again, so it's an example of a couple units of propylene and a couple units of vinyl chloride. Now in this example number C, part C, a monomer, I'm sorry, a polymer was given to us and we were asked to look at what monomer did we use. And the first one that you can see is a isobutylene. So this is a isobutylene, and the other repeating units is the styrene. So we have the two monomers. Now in example number two, remember the table we saw? We saw the table and we said this table is helping us to predict what kind of copolymer we can make. In part A, Professor Stevens asking us, what if we use aryl amides versus acrylonitrile? We look at the R in the table. The R for first monomer is 1.04. The second one is 0.94. So they are very similar. So if you make a copolymer from these two, so you're going to have a random polymer. You're going to have a random polymer. Next one in part B, we're looking at ethylene and we're looking at the methyl acrylate. And you can see the R reactivity for ethylene, this combination is very low, it's zero point 0.2, versus for methyl acryl is 11. So if you put these two together, you're only really going to have a homopolymer of this methyl methacrylate. I'm sorry, methacrylate, because methyl acrylate, right? Because it's really the reactivity is really high and this is very low. So we can say for sure that there's a big difference between the two. In part C, we're looking at butadiene and vinyl styrene. Again, look at the number, reactivity number for one butadiene is 34.5 versus for vinyl styrene is 0.034. So again, most likely we would have a homopolymer of 1,3-butadiene. The last, in part D, we were asked for the chloro-trifluoroethylene, very small, very small reactivity number, 0.005. And basically for comparing it to ethyl vinyl ethers, that is almost zero. So different polarity also with these two monomers. So we're really going to have an alternative copolymers for these two. Even though there are small numbers, they are similar. So let's go look at some of the formula we learned in this chapter. We learned two things. I call it big F and a small f. The big F is the molar, I'm sorry, is a mole fraction for the product, mass of the product, and a little f or a small f is a molar fraction of the feed. So this basically converting everything to one of the monomers, because we know the mole fraction of the two adds to 1. So we can convert the formula to one formula. We know from this, and then R1 and R2 again are the reactivity. We look up the butadiene. Butadiene is 1.35 for styrene together is 0.58. Now we know that we want this to be it's 1 to 1. So F1 and F1 is basically the same. So this becomes 1 to 1. Remember 1 to 1? Now we're going to have substitute the numbers. So 1 over 1 is 0.58, the R1, and 1.35 for R2. Again, because with the mole fraction is the same for both, everything is 1. So now we end up with 1.58 over 2.35, which is 1 to 1.5. The question was asked for the ratio of butadiene over styrene. So this we have to reverse this ratio here. Now we also learned some new equations, and that was Q. So we learned that if we have a Q1 and a Q2 for two different monomers, like for example, for these two monomers, and we have the Q and we have the what we call a E1 constant and E2 constant for these two monomers. So these are published reports basically. Now we learned that we can sort of predict reactivity ratio for these two monomers by looking at R1 and R2. So R1 and R2, we have a formula now. The formula is Q1 over Q2 E, which is base for natural log, to power minus E1, parentheses E1 minus E2. So now because we have the table, we have Q1 and Q2 for the two monomers. We have the E1 and E2. We can estimate the R value. So the R1 value would be 20 for this monomer. Do the same thing for a second monomer. So now we get a R value of 0.031. And we look at the uh, textbook, we can look at the polymer handbook, and we see the numbers are very close to experimental value. For the first one, we calculate R1 as 25. The experimental value is 20. For the second one, we calculate it as 0.031 and a little bit higher than handbook. The handbook is 0.015. Now, a couple of other problems, we look at it, and in this case, we asking simple things. Draw the structure for homopolymers, alternate polymers, random copolymers, AP blocks, and graph copolymer of styrene and acrylonitrile. If I show starting by A and starting by S and acrylonitrile by A. So the first question number, part A, is asking us the homopolymer. So homopolymer basically are the two connected to each other. Each one. In part B, we were asked alternation of copolymers. So we have SA, SA, SA. Then we're going to have in part C random polymers. So we could have A, S, S, back to A, back to S. In D, what did we ask for D? D asked for AB copolymer. So we have, again, all the A's and then S's. The difference now between A and D is that A, we really have two different polymers. One polymer is made of the styrene and one polymer is made of acryl. Here, the two are together, but the repeating units are AA and then SS and then AA. And the last one, graph copolymers. Remember, graph copolymers was we have one series of polymers like styrene here, and grafted to this styrene is acryl. Question number 6, asking us if you equimolar quantities of M1, M2 are used in azeotropic copolymerization. What is the composition of the feed after 50%? Again, remember this always the same. So M1 and M2 doesn't change. We have the equivalent of the two. In number 7, we're going to define R1 and R2. If you remember, R1 and R2 basically are the ratio of little k for reaction 1,1 versus reaction K1,2. So we're going to have these two rate constant ratio, and that really represent R1. R2 would be monomer reaction number 2 with 2 over monomer reaction of 2 and 1. So we're going to have a rate of 1,1 means monomer 1 and monomer 1 when they react to each other, with each other, over K rate for monomer 1 reacting with monomer 2. In R2 is the sort of the emphasizing monomer 2, so we're going to have to look at the rate of monomer 2 reacting with monomer 2 and reacting with monomer 2 reacting with monomer 1. So again, these are definitions for R1. R2 we learn in the table. Question number 8. Question number 8 is asking us if R1 and R2 decreases or increases during the copolymerization. Again, these are rate constants, so they should not change. The rate constants do not change. And then the last but not the least is asking us to look at the temperature on R1 and R2. If you remember from PChem, any K that we have, any K rate constant we have, is equivalent to a constant E to power minus activation energy over the gas constant times temperature. So the temperature has an effect on decay. Thank you for watching this, and I'll be back hopefully Wednesday to answer any question that you have.